Okay, we're going to have a look at the graph of y equals sine x, and you can see it there in front of you. Before I go any further, we need to define two things called amplitude and period. Amplitude is the distance between the middle of the graph and the maximum. So here you can quite clearly see that the middle of the graph, running straight through it, is the x-axis, and if I draw an arrow here like so, you can see that the distance between the middle of the graph and the maximum is 1, and it's the same between the middle of the graph and the minimum. Okay, it's also 1. So that's why there I've got the amplitude equaling 1 for this graph. Okay, because it's defined as also half of the distance between the maximum and the minimum of the graph. If I looked at distance of this graph from top to bottom, okay, it would be 2. From neg 1 to 1, I halve that, I get 1. So there's a couple of ways of looking about how you get the amplitude. So let's now have a look at the period of the graph. The period of the graph is the horizontal distance of one full wave. Okay, so if we look at the horizontal distance of one full wave here, that's the start of our wave here, goes all the way along there to 2 pi. Okay, so in that space we've had a maximum and a minimum, so that is one full wave. And I can choose the middle of the graph like that, or I could choose a distance between two maxima. So also that distance there, from neg 3 pi on 2 to pi on 2, that distance is 2 pi. Or it could be between two minimums, between neg pi on 2 and 3 pi on 2. So it doesn't really matter how I reference this, but the distance, horizontal distance between, for one full wave, is called the period of the graph. So there's the graph of sine x. It's got a period of 2 pi. It's got an amplitude of 1. Now it can be shifted up and down, and as you'll see in a moment, it can be dilated in different ways. But that's its basic shape. Its intercept there is 0. Also pi, 2 pi, okay, and then it would be 3 pi, 4 pi, and so on. And in the negatives, it's the same, negative pi, negative 2 pi, etc. Now, if we look at 2 sine x, the graph changes slightly. If we get the graph of y equals 2 sine x, so the coefficient of 2 out the front of sine x there, if we compare that with our previous graph, if I just put that on top of the graph that we've got now, like so, you can see that there's been a dilation here. And if we look at our original points, here, and here, and here, and here, have been dilated by a factor of 2 from the x-axis. So clearly we can see those points that used to be pi on 2, 1 are now pi on 2, 2. See those dilations there. Okay, so even here, if we look at this point here at negative 3 pi on 4, it's been dilated by a factor of 2 from the x-axis to there. Okay, so cut a long story short here, if you put a 2 or a 3 or a 4, okay, out the front, then you get a dilation factor. Okay, so let's write something down about that. If y equals a sine x dilation by a factor of a from x-axis. You might notice that the period hasn't been changed. The period is still 2 pi. Okay, so the distance for one full wave is still 2 pi. That hasn't changed. What has changed has been the amplitude. The amplitude is now 2. And if it was 3 sine x, we'd go up to 3 and so on. Let's have now a look at putting a coefficient in front of the x, what that does. Here we've got sine 2x. Now this doesn't change the amplitude. You can see here the graph is still maxing out at 1 and minimum of -1. Its period has changed, however. Once again, if I put the original graph back on, let's place it over the top of this one as best I can. You can see there the period has changed. The period of the original y equals sine x graph, the longer graph there, is 2 pi. Take that off now, we can see the period has been halved. Okay, so there it is. Original graph, period is halved. Now, there's a formula for finding the period, and I've put it down here. It's 2 pi over n. Okay, now what is n? Well, if the graph is in the form y equals sine nx, okay, if you place, and we'll work this out now, if we go period equals 2 pi over n, period equals 2 pi over n. So our n here, our number in front of x is 2. So it's going to be 2 pi over 2. That equals pi. So the distance for one full wave this time, and you can see it here quite clearly, instead of being 2 pi, is now pi. Okay? So that's our new period. What's our dilation factor here? Well, you remember that with the original graph, our maximum here was pi on 2. Okay, so it's actually been dilated back to the y-axis like that. Okay, so we can say here that, it's right up here, the graph has been dilated by a factor of 1 on 2 from the y-axis. Okay, all those original points have gone closer to the y-axis by a factor of a half. Okay, so that's when you've got a coefficient in front of the x. Now, what if we've got negative sine x? Okay, the graph then is reflected in the x-axis. Once again, if I put my original graph over the top here, okay, you can see if I just put the original graph there, it's completely been reflected in the x-axis. The point here, for example, is reflected down to there, and the point here has gone to the other side of the x-axis. So we've got reflection in the x-axis for negative sine x. A really tricky one is y equals sine 3x. And as soon as you see that coefficient of 3 in front of the x, you really need to use these sort of coordinates. The pi on 3 coordinates here, pi on 3, 2 pi on 3, etc. It's going to make it much easier to draw the graph. And in fact, you could even get a graph with pi on 6 divisions as well. A set of axes with pi on 6 divisions as well. What's the period going to be here? Well, period equals 2 pi on n. So it's going to be 2 pi on 3 is going to be the period. So I'm going to start, if I get my red pen back, if I start here at the origin at 0, 0, one full wave will go as far as 2 pi on 3. So if I mark in every 2 pi on 3, that's going to be the distance for one full wave. So if I mark in other key points, and this is what you need to do with these, I'll be able to draw the full wave. So here we go. Marking in all these little key points here, the maximum, the minimums, all the way through, just to make it a little bit easier for me to draw. I'm going to pause now and I'm going to draw the graph just because I don't want to muck it up and get a good copy for you. So just a moment. Okay, there's the graph of y equals sine 3x, and you see there my distance between for one full wave, my period is 2 pi, so 0 to 2 pi on 3 there. Next one's 2 pi on 3 to 4 pi on 3, 4 pi on 3 to 6 pi on 3. Same this way as well, 2 pi on 3 every time. So that's a tricky one, and as I said, I recommend that you set up axes with pi on 3 divisions for that. Interesting to note here, now what are these maximums and minimums here? Well, that maximum there would be pi on 6, comma 1, because halfway between 0 and pi on 3 is pi on 6. This one here, okay, would be pi on 2, comma negative 1. Why is it pi on 2? Halfway between pi on 3 and 2 pi on 3. So we've got pi on 3 is 3 pi on 6. No, sorry, it's not 2 pi on 6, beg your pardon. 2 pi on 3 is 4 pi on 6. So halfway between those would be 3 pi on 6, which is pi on 2. So hopefully that gives you a bit of a start into drawing sine graphs, and we can take things a bit further from there.